Alrighty. Okay. Thanks everybody for coming down here to. So yeah, if anybody that hasn't been here before, we've got a lot of new faces today. We're really excited to see all the brain power in this room. It is absolutely astounding. So yeah, thanks for all coming down here. This is Decentral or Decontrol as we call it. It's been a long-standing kind of like crypto hacker space that we've had since 2014. So yeah, it's been a fantastic space. We've hosted some amazing people down here in the past, some brilliant minds. You know, the brain power amounting that's happening here today might be at an all-time high, I would say. So thank you all for making that possible. Yeah, so we generally host a lot of different events, variety of different things through, you know, primarily Thursdays we have Ethereum Vancouver meetups. So we're usually talking about Ethereum-related things, anyhow. You know, so great to have this type of thing going on here today too. Yeah, basically we've got yeah, Nous that's gonna come, and Nous research is gonna be, you know, obviously everybody knows what's going on here, so that's incredible. But yeah, we're gonna just get into things here right away. We've got Bowen from as the chief scientist here from Nous Research. He'll start things off for us. If anybody has questions, it sounds like it's okay to just have an open kind of Q&A as we're going along. If you have questions, just put your hand up. We are live streaming right now, and that's on X. So if you're on X, YouTube, and Twitch. So if you're on yeah, if on X, look for DCTRL VAN, so Decontrol Van. That's where it is. We'll try and get to Nous to retweet it as well. And then that way you can check on any of that. But we are live streaming, so if you can just put your hand up, we'll get you a microphone. We've got 2 or 3 extras here, and then that way everybody can hear what you're saying, and we can get things going. So, okay. All right. Anything else you want to say? Yeah, here we go.
All right, appreciate everyone for coming out. Hi, everyone. My name is Jeffrey Cannell. You also go by eMozilla Online, co-founder of Nous, here with Bowen. And we'll skip all the bullshit except to say thanks for this awesome space. And let's start talking some optimization. All right, let's cool.
Yeah.
Let's go. All right, so what is demo? What is distro? We put out this paper like 6 months ago. We're like, oh, look, we did this amazing thing. And people are like, yo, show me the math. Understandable. All right, so we're here to show you the math, talk about why it works. So what is distro? It is a data parallelism and fused optimizer that can reduce the communication threshold needed for training models by like a factor of 1,000, 2,000, 5,000, somewhere in there. But why is that like actually important, right? So we kind of started this whole project of distro thinking to ourselves, what would happen if we never got Llama 4? What happens if we don't get Llama 4? What Llama 5? The open source community needs a way to like legitimately train competitive open source foundational models. That's something that has political ramifications. It has like on the ground ramifications for how much you're getting charged for models, like all of it across the board. We said like us in the open source community needs to be able to like from the start have a credible way to train frontier foundational models. And so we looked at it and we said like, well, what's actually the problem? Like, why can't we do that? And the reason that, like, the ultimate first stop reason was we have to be doing, like, these giant all reduces. And if there would be a way that we could actually, like, reduce the amount of communication that you need when you're training a model between the GPUs, well, what does that get you? It gets the ability to train all over the world. Now, this is important because it means you can train from different data centers. You can train with heterogeneous hardware. But, like, even more from that, it means that the scale of large data centers is a centralizing force, right? It takes power and it like brings it together into the few people who are able to amass this sort of power that can train with 100,000 H100s, 1,000,000 H100s, right? And if scale is all you need, then like eventually everyone but the biggest people are fucked, right? And so the question is, how can we make the all of us greater than like the one? And so that's what we started out as like the motivating factor for demo and for distro. And now we'll talk a little bit with Bowen about like how we actually got it to happen. So Bowen, you want to talk about like how we started?
So we started with actually that was back in February, right? It was we started working on something called zeroth order optimization, which is a gradient-free method of optimizing neural networks with only forward passes. And that method actually allows you to not send any gradients across accelerators because you only needed actually a random seed. And so with that, we actually saw that networks could converge, but very slowly. They were converging very slowly, but they could actually converge like together without sending basically anything. It was in the orders of bytes per step, right? but the problem was it was very slow. So then we thought, like, how can we transfer this knowledge of this little, so few information being transmitted to like a full gradient method with the backprop, right? So then we were like, oh, we could use something called a DCT, a discrete cosine transform, which is a decomposition of a frequency decomposition of the tensors where you can have orthogonal directions. And it's kind of like a random, it's not a random seed, but it's kind of a structured seed, right? A DCT is kind of the inverse of pure randomness. It's like an ordered basis, right? So you could have a random matrix or a fixed orthonormal fixed basis matrix. And so we could just transfer this knowledge we had to the DCT and compute the gradient first, and then send some of the DCT information. And we found that it converges as well as normal training, right? So I'll go. Do you want to talk more about anything, or I should?
Yeah, let's show them the goods.
Yeah. So this it's not really a presentation. I'll just go through the paper with you guys, and if you have any questions, you can just feel free to ask. Okay. So how demo works. So let's start with just a quick background, right? People have tried doing decentralized training or just distributed training in general, and the most limiting factor is the communication overhead. So you have to, in traditional training, you have to synchronize all the gradients between every node. So if you have 10 GPUs, you have to synchronize all the gradients between all 10 GPUs. And if you have 100, then it becomes 100 synchronizations, right? And this grows bigger and bigger when you have more and more GPUs and you have bigger and bigger models. And models of the size were at like 1 trillion parameters are very big. They're like 2 terabytes, right? A 1 trillion parameter model is 2 terabytes at BF16. And so every step you would have to synchronize at least 2 terabytes. That's the minimum. But usually with ring reduces, you have to synchronize much more, right? Or tree all reduces. So people have used methods like quantization and sparsification of gradients, which is good, but it's sparsification. Yeah, and you have a question? I heard someone. Okay. There are fundamental limits on quantization and sparsification. Is that quantization and sparsification are not tailored to gradient methods. They're just like a hack, right? You're just like, oh, what if we reduce the amount of information we're sending just by quantizing the vectors? And that works, but it degrades the training by a lot. There's also a low rank projection, which is you basically project all the gradients into a low rank representation and share the representation, which is almost equivalent to full rank training. But the problem is that this projection matrix is almost as big as the network. So then you have the second problem: how do you transmit this projection matrix? So you just sidestep the problem. And one of the solutions actually was to not synchronize this projection matrix every step and do it every 100 step. But this is also like very, it's like hacky kind of, right? Because you all still have this inherent problem of a very large matrix to synchronize. There's also federated averaging, which is something people have worked on, especially with DeLoco and DiPaco, where they train every model in individual islands. So every GPU just trains for some amount of steps, let's say 100 steps, and then we synchronize afterwards. So you let every model train for a while, and then you say, oh, let's synchronize. One of the major problems of this is that you have a trade-off of communication and convergence. So if you let the islands train too much, then they don't converge as well as full synchronization. But if you synchronize too much, it's still slow, because every synchronization still incurs the full size of the model, right? Still in the orders of gigabytes and terabytes. So what we've done with demo was that we thought about, what if we didn't need to synchronize everything? What if the networks could actually just be partially synchronized, right? So these 3 assumptions we had was just these 3. I won't get into too much details because they are pretty hard to explain. But if you read the paper, you can see basically how it works. So the algorithm is very simple, actually. We just get the local gradient. So this is the backprop. So we backpropagate and get the local gradient. And we do not all reduce, right? We accumulate into the momentum as usual. So if this was a momentum optimization, we just add it to the momentum. And then this is the distro step. So this is what distro adds, or demo actually, because distro it's a kind of demo version 2, let's say. And we're still working on it, and the paper will be out soon. But this is like the core idea behind distro is basically we extract the fast component of the momentum, and we remove it from the momentum, and we synchronize only these small components. And then we do a parameter update on everyone using like a very few numbers. And how do you extract these components is using a DCT. Oh, sorry. Okay, basically, you could use something called a KLT, which is the perfect decomposition. This is similar to PCA. So PCA and KLT are very connected. So if you guys don't know KLT, think of this as a PCA. They are very similar. So if you did the PCA or the KLT on the momentum, you would have the basis where you had the biggest components and then the smaller contributing components, right? And you can synchronize the biggest one. But we don't want to do that because doing a PCA or SVD is very slow. And still, you have to synchronize that DCT or KLT matrix, right?
Yeah, and for a little bit of like intuition behind this, think about this is essentially the same type of transform that's done with like JPEG images, right? When we have like JPEG images on the internet, we basically transform it into a specific frequency domain. We could and communicate only that. So you think about like a regular bitmap image, right? Like one bitmap is gigantic. Like a regular bitmap of every pixel is hundreds of megabytes, right? And that was like something like we just can't even look at pictures on the internet if you had to transmit like hundreds of megabytes of every picture, right? But it turns out there's a whole bunch of information that's like essentially like not needed to transmit the idea of what's in that image. And so a lot of these ideas actually came out of like 90s era optimization, and we're now like applying them to what we're seeing in like the actual training dynamics when training a model.
Yeah, the DCT is exactly used here as is in JPEG, because if you can see, we chunk the momentum tensors into like square or like rectangle chunks. For example, in our 15B run, we did 128 chunks. So it's like 128 chunks of size 128. So JPEG uses 8 by 8, right? And we used a 128 by 128 DCT chunk, and then we picked the top case. So the coefficient of the DCT, we picked like, was 4, right?
We did 4 for the big one, yeah.
4. So if you think about a 128 by 108 tensor, and you only pick 4 points. So it's like a 1 over 128 squared compression, 4 over 128 squared. So it's a 5,000 or something, 1 over, yeah. And so basically we just pick those DCT frequencies and only synchronize them, right? So if we go into the code, you can see here is demo is very simple. Yep. Is this good? Maybe the line number. Okay. So here you have for every group. A group is just a tensor, like in kind of. Oh, what happened? Oh no, I don't have internet.
Oh no. GitHub tried to refresh it, I think.
Oh no, yeah.
Yeah.
Yeah. No, it doesn't. It's dead. Okay, but
it's fine. Don't worry about it.
It's fine. It's fine. That's sad. But yeah, okay. Let's just go over it on the paper. Yeah. So the only change we made at the end for training LLMs is adding this signum optimizer, which is basically taking the sign of Qt. This accelerates the gradient descent. It's basically a version of, it's kind of ADAM, but when you set the beta 2 to 0, when it approaches 0. So a signum is kind of like a special version of ADAM-W. But yeah, and we trained a 1B model here on the paper, and we used we swapped the ADAM-W optimizer with the demo optimizer. We didn't change anything except this special hyperparameter called beta in demo, which we set to 0.99. And we trained with 64 H100s and 100B parameters, and you can see here the losses for 1B. You see the cursor? Yeah. The 1B, this is ADAMW, the red line. It converges pretty well, but our demo one just converges faster. We don't know why. We're just assuming it's some kind of regularization or something. Yeah. So maybe it's up. You guys can help finding out how this works. And this is also the eval, so it wasn't overfitted. So this wasn't like some kind of overfitting because this is the eval set. So everything you can see here, ADAMW is the red line, and our demo is just like demo optimizer just goes higher on HelaSwag, Arc, Easy, and Pika, and just lower on loss, right?
So I guess, like I said, a motivating kind of intuition to think is demo works because rather than sending the whole picture, we're sending JPEGs of the gradients between all the computers. And
of the momentum.
JPEG of the momentum. Yeah. And that's basically why we're able to reduce the training volume. And again, this is important because then we can finally now actually train models over the internet, give the open source community like a credible way to stay at the frontier and to have uncensored and unlocked models still, available to everyone when there's all these centralizing forces that are existing in the world right now that are trying to drive AI into the hands of like a very few select group of people. And so insofar as we can stop that, let's do it, boys. All right, so if there's any nerdy questions, we'd love to hear them. Let's do it.
Yeah.
What's up? We're gonna do the mic thing for the live stream.
Hey, well, I actually have a lot of questions, but I'll stick to one.
Can we do one? Yeah.
Yeah. So my main question is, so you're only synchronized. So DCT, if you didn't truncate it, it would be perfectly reversible and lossless, right? But you're only synchronizing like a small chunk of that.
Yep.
So did you compare against like a model that's just scaled down to be like the same size of data that's synchronized across the computers? Because in some way, if it's like perfectly encoding, then isn't that the same as if you're just training a smaller model?
Well, it's only on the gradients and only on the momentum. So I'm not sure it would be exactly the same.
It's not exactly the same because when you're training on a smaller model, the model has less capacity. But here, every step you can send any of the DCT coefficients. It's not limited. It's not like we're limiting the DCT coefficients to be only in one place, right? It's a full. We could send everything after a amount of steps, right? Because in the momentum, you're still accumulating data here, right? Every time every step, you're still accumulating information of the gradients into the momentum. It's just you're not sending it yet, right?
So there's there's a hidden momentum that every accelerator has that's independent. And basically what happens is as it accumulates its own learning from the only data that it was given during the assignment, basically like things start to bubble to the top, right? And that's what the top case selection is going to do, is like once it's learned enough, it'll like bubble to the top and say, okay, I've learned something significant enough that I need to contribute it to the rest of the accelerators. And then that's basically the way that like we let the top case select them. And that top K can be anywhere within that for each parameter, the top K can pick any of the indices within it to actually transmit.
Yeah, so it's still a full parameter training. It's not like limiting to some subset of parameters.
Yeah.
Cool. Thank you.
Awesome. That's cool. Yep.
Have you compared this at all to the MinGPT speedrun optimizers in terms of like wall clock time and like how many steps to converge and that kind of thing?
The MinGPT, I don't think we used.
Or NanoGPT.
No.
Yeah,
so this was very much eliciting like the training dynamic. Like we're interested in like the training dynamics here. So like it probably right now, like the code that we've released is actually fairly unoptimized, and it's probably like it's slower. Like you have to move some things back to the CPU. So it wasn't like necessarily being like is this the fastest, absolute fastest way, but more like what does it tell us about the training dynamics that you only need to transmit so little and still get convergence? So we still have a lot, and that's honestly why like we're finally like, all right, let's get it open source, let's get everyone at least being able to look at it, because there's all these like areas of discovery that we just were like, now we can let the community work on it.
And I would just add the DCT is the only thing additional that it does, right? So the DCT is extremely fast because these chunks are very small. It's 128 by 128. And it's like if you had a dedicated kernel for the DCT, it would be 30 milliseconds, right, for 1B model, or like 500 milliseconds for 1T model. So it's negligible, basically, on the order of the training when you train. Because when you train, it's like 10 seconds per step, or even more, 30 seconds.
So we're working on like some CUDA kernels as well
Yeah,
to
yeah.
actually do this fast and get it out.
So it sounds like you're using the DCT on all the parameters and
Mhm.
syncing the ones that bubble to the top in terms of what's happening locally
Yep.
at each one of them. Is there? Do you
On the
think- do you-
gradients, on the gradients.
gradients,
The momentum.
yeah.
Yeah,
Sorry,
yeah.
The
momentum.
momentum, which is
Gradient-
from
yes.
the gradients,
Yes.
yes,
Yeah.
yes, yes.
Do you think it would still converge if you partitioned, like, not determined, not like human determined, but if you had an algorithm to partition either layers or subcomponents of layers of the network and their gradients, and shared it, like did an all reduce on a subset of the network based on the highest change to gradient or momentum?
Yeah, so we did actually work on something basically like this, which is like a dynamic compression, which looks at
Yes.
the like energy rate of each of the parameters and selects from that.
Right.
That's one of the things we're working on for like the next kind
Okay.
of version of it. But yeah, so this is a naive one because it actually is a for loop over all the parameters
Yes.
and is selecting a constant sized. We have this like top K parameter that's the K in the top K. We're picking the same number for every one of the parameters, independent of like whether it's the embedding layer, or it's the layer norm, or like it's the MLP or whatever, like whatever it is. So it's kind of one of those things where we were like, the fact that it still works even under that like naive assumption, like that naive thing, tells us that there's like more to be discovered within the training dynamics, and that there's a lot of like low-hanging fruit that can then be used to improve it. So
Yeah.
Yeah,
The,
you probably
the perfect case would be doing the PCA or KLT on the full network, but that's too slow, right?
Yeah. You
But-
probably
but
get one
yeah.
or two more zeros with that.
Sorry?
You probably get one or two more zeros with that optimization.
yeah. I don't want to take too much more time, so we can do one more, and then we can get on to this one.
Yeah, thank you. You're extracting the fast components from the momentum.
Mhm.
Can you give us some intuition exactly of what a fast component means?
Okay. Yeah. So by fast here, we mean when the momentum, when the gradient are accumulated into momentum, right? There's some parameters that are very big, like just the momentum. They don't really need the momentum because every step they're always moving towards one direction, right? But there are some parameters that are going back and forth. They're like moving a little bit to the right, sometimes a little bit to the left, and those are
slow moving.
Yeah, those are slow moving because when you add them to the momentum, after a while they go towards one direction very slowly, right?
So they're basically just like values that are high in the moving average.
Yeah, but there's a difference also because if this principal component is like moving back and forth the same amount, it's still a fast moving, even if it doesn't move, right? Because if it moves right by one and moving left by one, it's still called fast moving, but it's oscillating. It's still,
So
on average, it's still not moving. So,
Okay.
but we're really talking about the
Almost like the
every
energy or the
single step.
excitement, like the
Yeah,
energy
yeah,
or the
yeah.
excitement of it.
yeah, exactly. The energy or kind of the excitement of the.
But the DCT is only instantaneous, right? It's
Yeah.
only one step. So
One
how does
step.
it know about the oscillation?
It doesn't.
It doesn't. Okay.
It doesn't. Yeah. So if every step there's one parameter that moves a lot, right? The DCT would encode that, and you would move a lot on this step.
And this was basically one of our conjectures that we kind of went over, was basically that you can bifurcate into like these that there are fast moving components and slow moving components that eventually become fast moving components after they've been accumulated into the momentum. Now, to be fair, this is something that like we did not prove mathematically. We don't have like we don't have a mathematical basis. All this was given this as like an empirical basis, we got this result.
Yeah.
So
If this was true.
yes.
Yeah.
Yeah. All right. Well, thank you very much. I'm Jeff. This is Bowen. Thanks for hearing our talk. All right, Jeff number 2. Also, if anyone doesn't know, I don't know if it got here yet, but we're bringing a bunch of pizzas. We also have all drinks all in the back over there behind the door, so feel free to grab anything that you want.
Yeah.
Yeah.
Thanks.
Yeah, we've got. All right, and we've got another speaker here right away, so don't.
Thanks.
Yeah, perfect. Oh yeah, sure, of course. That might be your second your background. Yeah. You just have to change your which screen it's on. It's like doing an extension. Drag that window across. That might be the simplest. Yes. Okay. Yeah, perfect. It's okay. Okay, you're up. Okay. All right, everybody. We're going to get started again here. All right. Simmer down. We're going to get things going again. All right, everybody. If you can find a seat or just calm down, we're going to speak again here. We got another one. We've got another talk. All right, everybody in the back there. We're going to get going again. We please have everybody attention. Everybody, we're getting started. Thank you. Hey. All right, big round of applause for our for Bowen, our last speaker. And I'm just gonna get a little bit of a. We're starting again here, folks. We're starting again, so if we could just calm it down in the back here. If we could just quiet down. We're gonna get started again. Shh. One big shushing. If we get one big shushing, would be fantastic. All right. Yeah, thank you, Bowen. And now we're going to get started here with you. Sorry, what was your name again? XJDR. Okay, we've got XJDR is on here next, guys. So, yeah. All right, let's take it away.
Hey! Hello, hello. Hello. All right, so we're talking about uncertainty at inference time, but more specifically, what the fuck is Entropix anyway? So a few weeks ago, months ago now, we were working on inference platforms, and Doomslide on X kind of talked to me about, have we looked really and explored the entropy of the distributions? And that kind of is what spurred all of this. So let's think about transformers in a very simple way as a function that takes some sort of context on the way in and then outputs a probability distribution over all of the possible next logics. Very, very simplistic view of it, but very easy way to reason about. Well, when we have those probability distributions on the output, that tells us a lot of information that we don't really use right now, specifically about how sure we are about the entire distribution, how sure we are about certain points in that distribution. So the very, very basic concept with all this was, if we use the tools that we already have to understand basic probability distribution, could we get some more information about what the transformer actually thinks and knows, and use that to get better answers out? Very simple, and kind of makes a ton of sense in hindsight, but up to this point, no one really had done anything with this. So what we started looking at was the Shannon entropy of the model, or of the output distribution and the probability distribution. And what we wanted to specifically look at was how much uncertainty or surprisal is there in the logits. So the supposition was, if there's only one or just a few logits that are very clear, then we should just be argmaxing. We should just return that one. Let Jesus take the wheel, go with God. And that does surprisingly well, but it's surprising how often that isn't the case with the transformers. And so it comes to really reinforce that all tokens are not created equal. There's some very low entropy tokens that are very easy to predict. There's some that you actually have to spend some more time on. And so what we thought about was, okay, when we have to spend some more time on those tokens, what are we actually thinking about? What does that shape look like? And one shape was, if there's just very low probability distributions, if the model has no fucking idea what it's looking at, why are we just blindly sampling inside? Why do we take a bunch of low probabilities and return a random one? That seems like a very bad way to run. And that's where a lot of hallucinations come from. Like, we know the model doesn't know what it's talking about. We just sample and return anyway, blindly. So our thought was, well, what if we could resample or backspace there and not return that? What if we could go back to a point where we either said the model's confident now, or we don't know what the answer is, purely just on what the model thinks. And I want to be very clear about this. It's not giving the model superpowers. Shit in, shit out. If the model's trained poorly, it's going to be very confident about the wrong answer. But you at least understand what the model is confident about and what the training data looks like. So that's kind of, if you looked at the Entropix freak bow, this is kind of describing the 4-quadrant group. But then there's another one that's the most interesting, is what if it's confident about a subset of things? Well, that's a really interesting area to start branching. So let the model explore, and let the model start kind of processing each of those ideas in parallel. Let's see if we can return the best one. And the best one being, on aggregate, can we find a very high probability way to look at this? But probabilities alone isn't going to get you there. You actually kind of want to understand the entropy space of it. And this is kind of where entropy alone wasn't good enough either, so we actually had to look at the variation in entropy. That's where this whole thing kicked off. Now we have a two-dimensional plot that we can look at entropy and the variation in entropy. Start giving us some really interesting ideas. And this was kind of the basics of the experiments that we kind of went through. And just to be very clear, Entropix is very much in the research phase. We think there's a bunch of really good ideas. We have some really promising results. These are not conclusive findings yet. We're working towards that, but right now this is very much, these are very interesting things we found. These are very interesting things we've measured. These are things we're looking at, and we think that they're very promising directions. So the very first thing that we noticed was when we started fingerprinting models to plot their entropy and variation in entropy across a variety of input prompts, you started to see these beautiful base models with very high concentrations of entropy density. This is a pretty good fingerprint of the entropy density of the training data. And when I say entropy density, there's just a bunch of cool ideas in there. There's a lot of information contained within these bits. There's not a lot of AI slop. These are a lot of unique, novel things, but you see this very high density of entropy information and very low variation in entropy. So it knows what it knows and knows a lot of interesting things. Then you look at a trained model, an instruct-tuned model, and you see an entropy collapse. The variation in entropy goes way up. You see a huge dispersed diffusion of this. The model is not happy anymore. And that's where you get weird hallucinations. That's where you get the AI slop. You get models that have, if you're inside the training band and the policy, you get interesting and repeatable information, but you don't get creativity. You don't get lots of problem solving. You fall into these local basins. And this is what I said the first time I saw this. They took this beautiful training data. They took this beautiful base model. They massacred it with safety alignment, with instruct tuning, with very, very heavy-handy RLHF. Exactly. Look how they massacred my boy. And this is where you see, this is what the small model smell looks like when it's not creative. This is where you get the AI slop of just repetition over. Entropy collapse is what kind of separates the AI from an interesting output. When we started plotting these, we started noticing that we got really, really interesting distributions if we just plotted them on a two-dimensional grid. And this shape is insane. There's no reason this shape should exist. This shape exists for just random inputs. We can just throw random tensors into the weights and we get this shape. This is a fundamental property of the weights in the training data. No idea why. Still open area. Not yet, but I'd love to. We're good. Shannon entropy and the average variation in Shannon entropy.
To repeat the question, I was wondering how you define the variable that we're seeing on the vertical axis, so the variation of the entropy.
Yeah, we can go into it a little further, but if you look at the repo, the comments are all the math and latex is in the comments on there. But it's
Cool.
the-
So you said it's a variation
of the entropy,
across.
the logit. But this is all looking at the logits.
You're looking at the logits for one token,
Yes, yes,
and so it's a variation of the entropy
correct. Over the entire sequence.
over the sequence. Got
Yes.
it. Thank you.
So there's a time component here. If you look, there's a repo called LLMMRI, which has a 3-dimensional plot. That third dimension is time sequence, so you actually get more depth in here. But this is an interesting way to look at these plots. So when we started,
Thanks.
yeah, no problem. So when we started this research, we had the very naive 4-dimensional quadrant where we just said, hey, if it's low, argmax. If it's high, resample. If it's middle, just do min p or whatever. We knew that was naive, but it was just a very good way to reason about it from a logical standpoint. What we found is if you look at these beautiful little plots, these are actually a very nice Dirichlet distribution. And if we sample and you find a point, you can ride an optimal entropy down while you're reducing var entropy. And those tend to make the model more sure about an answer while still preserving the creativity, while still preserving the interesting parts. Now, high entropy by itself is not a good thing necessarily. For code, you want typically low entropy information. There's only so many random subsets of tokens that will work for the syntax or that will solve the actual problem that you have. It's math, only 9 other tokens that can be in the next character, whatever. But you can start seeing that even when you plot any of these in these curves, in these distinct curves, you can start writing that slope down to get to an ideal entropy figure for a given model. And these are 3 different models. Again, no reason this should work. This is a Llama 70B where you see these very clear gaps, and you see these very clear lines where when it knows something and it's sure, and then you see the space between the gaps where you don't want to be, and you want to move to one of the orbits or the none. This is the deep-seek light. You start to see these weird combing effects, but you still see the grids and the gradation. This is the only Mo we tested. That might be a function of the Mo as well. And then this is Quen, and Quens are really weird here because they have very long sweeping distributions. They can maintain high variation in entropy, but still kind of ride that plot down. So if you look at main right now in the Entropix repo, we have this thing called dslider, which actually moves the logits to be within these distributions. That's fucking hard. You have to tune it per model. You have to understand and find these slopes. You have to find these slopes without the a priori information. You have to tune like 38 coefficients. And so far, we've been able to get it to be really creative, but not necessarily technical, or really technical and not so much creative. So there's a trade-off. And that's not useful for anybody. But it proved out the information, and we got incredibly good results when we did take the time and effort to work on it. So,
Just Kevin, one to the.
oh, we go.
Usually when these kinds of patterns show up and you don't know why they're there, it's because of a choice of coordinate system or
Yep.
units or something like that.
Yep.
I'm guessing you're going to show like amazing results that show this like curve writing is meaningful, but like, do you have other explanations?
Yeah, so like this is just a function of how it's measured. It's like the exponential is why it's in the curves. Like there's generally functions of why it's there, but these clear delineated gaps and then the diffusion coming up, there's no reason why that should be there.
I see.
So like you can fit this into, like it's very easy to fit these bands as a function of just the equation that we use to measure it, but these gaps and these clear delineations, there's no reason why, like those are provably a byproduct of some aspect of the weights, the latent space, whatever.
Gotcha. Thanks.
So we decided dslider was too complex, too hard to meaningfully make progress with. It might be the way that we end up going, but we kind of worked on, is there a better way that we could plot this? This is where we went to Arrhenius distributions. And I don't want to get too far into this because this gets into some asylum math. But essentially, you can plot some very dense momentum in the middle, and then you have tails on the outside. If the middle density is growing, then you're more sure about it, and that's when you branch. The tails are growing, you have more noise, and then you can figure out I either need to resample or I need to argmax. This is a much more convenient way than looking at all these coordinates and all of these different plots to kind of get to the same type of gating information. This also lets you look at multiple moments, so you get a lot more information about this. In a very convenient way. This is, again, a lot of dense math that you're welcome to look up, and it's very, very well documented in the repo, but for the purposes of this conversation, all we need to know is it tells you when the density grows in the middle, you have more signal, tells you when the tails go up, you have more noise. So we want to increase signal to branch, We want to reduce noise possible, but if we get a lot of noise, we either resample in backspace or we let Jesus take the wheel and argmax our way out of it. So this is the drum roll. It works. Works pretty well. And we're seeing these kind of numbers across a variety of model sizes. Now this is where the why don't you just fucking release the benchmarks conversation goes in. Most benchmarks are measuring log probs. We're actually sampling, so log prob measurement doesn't actually work super well to measure a sampler, to evaluate it. If you want to measure the sampler, you need to do string matching typically. There's other ways of doing it, but generally you want to do string matching. That means you have to write fuzzy matchers. You actually have to have the string that's the correct string to sample. You have to figure out if you want exact match or fuzzy match. We have to write all this shit from scratch. Not only that, we're trying to measure a whole bunch of different things. We want to measure if we can get to a point where we're predictably saying, hey, don't sample a bunch of low probability logits. We actually want to measure the hallucination mitigation and reduction. We want to be able to prove that we're actually mitigating hallucinations on a measurably and statistically significant level. It's a new eval, that doesn't exist. We want to prove that the branching has the nebulous log plot ability where the farther we branch, we have some sort of linear performance increase, otherwise it's just wasted flops. So a lot of this is just, we have to establish reasonable baselines, we have to figure out what exactly we're measuring, what are we benchmarking, why is it interesting, and for the most part, we have to write these from scratch. But because the angry mob has spoken, we are benchmarking against normal benchmarks that are not that useful for us, but it's interesting for other people. We do it across a variety of different things, and we're seeing more interesting improvements, but we see improvements across the board. These aren't trade-offs. MLU Pro is partly the benchmark. We could tune it better for that. This was done in a day. So the nice part about this is our core code is thousands of lines of insane jacks that I wrote that mere mortal shouldn't look at. I can't even look at. It's terrible. This is all in PyTorch using transformers. So this is something that everybody can look at, everybody can use, and we're going to publish this to local in the next couple of days. It just needs to be cleaned up. So this is a simplified version of our system, but it's something that should be able to plug directly into transformers, VLM, SGLang, whatever. You should be able to see these types of results, or not, and we can talk about it. And this is kind of the plot that we're seeing over, and we can see this over a variety of model sizes, but we're going to have some more detailed information about that. I was going to run a live demo, but I can't maintain the connection to my SSH system, so we're just going to show some interesting output. This is insane for any model. This is something that O1s and 4.0s kind of mess up consistently. But you start to see some, read the bottom, human intelligence is not designed to think logically, so it does not have the ability to make decisions or make predictions based on the information provided. I just don't disagree, but that's not in the training data, I don't imagine. So we're starting to see some really interesting entropy preservation. This is obviously correct. It's ignoring the information in the prompt. This is saying, I have these amount of kiwis, but 5 of them are lower than average. How many do I have? Almost every model reduces those 5 from the total. It's just a very clever way of looking at how the attention works. It sees 5, it sees reduction, either does an average or reduces the 5. It gets the right answer. This is something that Sonnet and No1 have only been able to consistently do. This is Quen 0.5b. This is a 500 million param model. This is fucking insane that, and we can get this consistently. We can also, this is also Quen 0.5b coder, where it will provably check, it's the same question, but it will check the Python and it's correct Python. So this gives you the ability, it's cut off a little bit. This is Python and it's correct, trust me. It gives you the ability to actually prove out in the sentence, and we can drop the low var entropy system to just argmax it and actually get the right code back out. So we're not sacrificing that for how we pull this data out. This is also, you can tell it's 0.5b because it's the Quen formatting, but it's also answering, reasonably difficult math questions very consistently, very concisely. It's not getting into loops. It's not getting into reasoning loops. It's not reflecting and going back. This is just sampling information from the core data that it knows very well. More fun stuff. This also transfers. The exact same coefficients, the exact same code. This is on Llama 8B, and you can see that it also answers correctly. It's concise. This is something that Llama 8B was not trained to do explicitly, but it's in the training data, so we're able to pull it out, but make it confident. You can see here, it does all the quadrants here. We had some injections, which is make it think. We're not using the dots here, but it's injecting still. And then branch, it found 2 different options. It explored the branches and returned the best one. And the score is up top. It's cut off of the screen, but there's a score up there. Yeah, more of the same. It does cool shit. It works. It works across models with the same coefficient. We don't have to tune per model. We don't have to tune per output, and we're really excited about it. The thing that we're most excited about is proving that this branching works and works pretty well will allow us to plug in something like QWQ, which is what I was going to do the live demo on, to actually make an inference time, test time compute system without training it in. So being able to approximate the O1 style branch out for test time compute to have the longer we think about it, the better the answers are, without having to explicitly train it in or have a custom inference. So this branching can be bounded, but can go as long as you want. And we think that that's how we're going to unlock something that looks closer to O1 in the open source community without having to reinvent any of the wheels or retrain all the models. Really excited about QWQ, really excited about R1 because those are natively suited for this. So while this works with, 8B, we've tested it on Nemotron 70B. This should work especially well for QWQ and R1. It does for QWQ. There is a demo. We'll release that code. But yeah. And then we're already starting to get cited in some stuff. There's a couple papers released today that were entropy-based that didn't cite us. This is a DeepMind paper that cites the Entropix repo. This forking paths is essentially a restating of a lot of what we're doing, but more people in the industry are using this, thinking about this. This is going to kind of become, I think, more accepted, and super excited about it. Questions?
Sorry, could you walk us through your intuition behind using both entropy and the variation in entropy? Sort of like intuitively, what does it mean to be like where would you want to be in that trade-off? And I guess from a design standpoint, what led you to want to explore those 2 variables?
Yeah, so kind of intuitively when people have used this in the past, low entropy good, high entropy bad, generally. That's not necessarily true. High entropy sometimes really good for creative writing, for narrative consistency, for creativity and problem solving. Sometimes low entropy is very good for structured output, for JSON. So just looking at the entropy itself wasn't enough to really get any deep intuition without plotting how confident were you in that picture. And variation in entropy is a good way to plot the model's confidence in, I'm very confident in like these 7, 12, or I'm all over the place. I have no idea what's going on. It allowed us another axis by which to measure how confident the model was. And the entropy gave us more picture of surprisal or how many different paths of things. That was the real unlock here, and the very initial part was entropy alone did not give us a full enough picture to make meaningful deductions and conclusions off of. Needed something else, needed another axis to measure out. Variation in entropy ended up working out super well. It's not the only thing we tried, it's not the first thing we tried, but it's the first thing that worked.
So I guess the intuition is that variation in entropy is, you're saying it's more or less a proxy for the model's confidence
Yes.
in the answer. Could you walk us through that intuition?
Yeah, so like low entropy, low var entropy, but with a single probability means I'm very confident in this answer. There's not a whole lot of other answers. That's when we go to argmax, right? High variation in entropy, high entropy, and low probability means I have no fucking idea what's going on. Please resample. Please go back. High entropy but low variation in entropy means I'm pretty sure about these 7 things, but I don't know which one is right. So branch, kind of go through those outputs. This is a way that we can look at it mathematically without having to understand the context. We're kind of letting the model, the training data say, I'm confident about these, confident about this one, I'm not confident at all. And this is really, it's a per token strategy for sampling, but it's also a way to do some sort of mechanistic interpretability of the model of like, tell me when you're confident, tell me when to branch, tell me when to just argmax. Like if you know what you're doing, You don't need to waste resources. Just turn it. It's a good way to every single token, look back at the model, look back at the process. Don't just blindly sample with a single strategy going forward, and backspace if you get into local max minimum. So it's just the intuition is the model has a lot more information than we're using. Each token is a whole new adventure. All tokens aren't created equally. How much information can we pull out of this based on what we know? For the most part, it's just log probs, just the entropy of those. What can we suss out of that? And it turned out it works fairly effectively.
Cool, thanks.
Sounds like when you're backtracking or branching, you're probably just going down the list of logits and the probability list.
No, we resample. So there's some other momentums that are happening internally that you want to actually recalculate the distributions. So specifically what's happening for branching is we return top K of those in a single batch in a forward pass, but then each one of those calculates its new momentum again. And for backspace, we reduce the cur pause, but then we set the probability of the sample token to negative infinity so that it won't resample again. And then we keep backspacing until either reach a max backspace level, want some control, or we get to a good entropy picture, or it says I don't know, because the only thing that hasn't dropped is end of sequence token.
Right, and have you experimented with just adding hard-coded tokens like or?
Yeah, so that's what inject is there.
Right.
So we have a sequence of those and tokens that we inject. It really looks like O1 has those attention sinks. I don't think that those are trained in. I think those are a function of just how the RL works. Like it's a convenient byproduct they had. If you train those in, I think you wouldn't inject them. But if you don't train them in, you can find these attention sinks where the model is more inclined to pivot to something. Wait, ... was the original one for Entropix. Those seem to be unreasonably effective, but it does take a lot of trial and error. They all kind of look the same from when you look at them, from the probabilities, from the attention activations. But I did a grid search of like 1,000, and I found one that worked pretty well, but it worked unreasonably.
Cool, thank you.
And that was ... space.
All right, so you mentioned that this is particularly like the entropy like collapse is mostly for like instruction tuned and like RLHF models. Does this particularly like Entropix work well for base models? And also, do you think this is just something that needs to be fixed in that sort of process, instruction tuning and RLHF? Or do you think this will always be something that should that's like inherent in like the way that you should sample from these models?
It should be fixed. This is a abomination. It's a catastrophe. There's no reason for this. I don't think people are looking at it. I don't think it's like a lack of skill or anything. It's just not. It wasn't a consideration when these are trained. Making entropy preservation as a loss objective would fix this pretty easily. I'm oversimplifying it drastically, but having that as one of the coefficients for the optimizer would fix a lot of this pretty easily. Doom Slide's kind of dream is that you never touch the fucking weights and you just sample from the base model directly by using more sophisticated control vectors. Basically, you don't have a dimensional reduction in SAEs. You do something that's more fully pictured, that has we have some code checked in with VMF where we plotted on a three-dimensional sphere. But the dream would be you have the base models, you manipulate the outputs based on the entropy distribution, and you get magic afterwards.
Awesome.
Hey, have you looked at like fact knowledge and where in that chain, knowing that like a knowledge cutoffs, you know, of I don't know, December 2023, and plug in some facts from, you know, modern day that you would know, and be able to identify exactly where? Or is there a little bit more of a entropy drop off at a point at a specific token or in that fact range?
Yeah, you can see. I don't have any tests for this, and this is more where smaller models aren't as good. But we've run experiments where it's a RAG trigger. So like when you get to a certain entropy place, it triggers a RAG optimization because it's unsure. That's a dimension that you do it. Like it doesn't tell us that we need RAG, but we know that it's unsure. So RAG can be a way that you supplement that. We don't have as much interpretability on the token level yet, but that's a thing that we are working on. That's just takes a lot of tokens, a lot of labeling to go into that. And there's a great community. Actually, I want to shout out Sinatras and Doomslide for doing a lot of the Lord's work on this while I was out here enjoying the conference. So they helped put it together. So huge shout out to them.
And then one other quick follow-up. Is there implications on the training side of this that you think are
Yeah.
important in terms of,
As many as not
gauging
more.
it as you go?
Yeah, as many as not more. You could do entropy preservation. You could do better knowledge retention. You could train out hallucination, or at least mitigate hallucination as part of the RL AIF and RL fine-tuning trains. There's at least as many, if not more, implications for training than for. Sorry.
All right.
Yeah.
Sounds good. All right, everyone. Just want to say real quickly, thank you to Central for having us here. We've got drinks, we've got pizza, and let's talk about how to keep AI in the hands of the many and not the hands of the few. Let's go.
Yeah, awesome. And thank you everybody for coming out tonight. Like I say, we're doing events regularly here. So if you guys are in Vancouver, I know there's probably a lot of you that are just passing through and saying hi. Whenever you're around, please just follow us. Follow along. If you just follow us on Twitter, it's DCTRL Van. We're always hosting events all the time. There's a lot going on in the city. We're a little more crypto focused than we are actually AI. But obviously, there's a huge intersection here, and just looking and seeing it, like what's happened here tonight. I'm really excited about AI. I got really inspired tonight. So half this stuff I don't understand, but it's incredible to see the brain power here and see what you guys are working on. So thank you all for coming out. Please check in. Every Thursday we're here for sure, and we've got a variety of other things. For any of you that are interested and are collecting POAPs, who knows what a POAP is here? Oh, we got a few POAPers. Excellent. So there's a little black poster back there that's right by the doodles. There's a little tag there, so if you just tap your phone on it with NFC, and you can claim a POAP that says that you were here tonight for the Nous research. Okay, feel free to stick around. We're going to play some tunes and have some food and drink. Thanks, everybody.